You have to let me know if the water...
This is there's nothing real particular about this location. It's just
My name's Kevin McGuire. I'm a professor at Virginia Tech, so not so nearby, but I did live here in Plymouth for a little while and worked with the Forest Service before heading to Virginia Tech. And Mark Green.
And when Kevin went to Virginia Tech, his position opened up, and I ended up getting that. So I'm now at Plymouth State, half Plymouth State, half U.S. Forest Service, as a research hydrologist here at Hubbard Brook.
So Mark and I are both hydrologists. That we do focus on some different aspects, but we collaborate quite a bit. And I guess our thought today was we would start by talking about some small watershed ideas and a little bit of the history of the Hubbard Brook Experimental Forest. We're hearing a lot today about the history of the ecosystem study, but we'll take you back a little bit further to the experimental forest. Talk about small watershed studies, and then some of the things that we're doing now and plans to kind of move out into the valley and kind of really look at the hydrology of the Hubbard Brook watershed, the whole watershed. And Nick Grant, who's over here on the bridge, he's the hydrologist with the Forest Service, and he's been working on gauging the main Hubbard Brook, something we started a few years ago, and we're now finally getting to gauging the brook itself. So we'll end up there as we walk down Camp Dog Road. But the first thing to kind of think about is, why was Hubbard Brook Experimental Forest established in the first place? After the turn of the last century, you had the Weeks Act and the establishment of the National Forest here in the east. And probably a couple decades later, there was the Omnibus Flood Control Act that really got the Northeastern Experiment Station at the time out surveying for flood-related issues and looking at land management and flood interactions. And I think that the folks that were doing that surveying were frustrated with the lack of data. So that was 1936, I think, was the act, and that work probably carried into the 40s, maybe to the early 50s. At that time, other experimental forests were established elsewhere that had a watershed or hydrologic emphasis, where they were looking at the interactions between forest management, and water and sediment largely. That information wasn't here in this region, and there was a push to get that information. So the development of the Hubbard Brook Experimental Forest was really for that purpose, was to collect scientific information related to water yield, peak flows, and sediment related to forest management. So a lot of what we heard about this morning with the ecosystem study came along a little later, about a decade later, after the establishment of the experimental forest, which was established in 1955. The weirs were built that year, and the first data was being collected in about 1956 with climate and streamflow data. So that began the record, and there were planned experiments. When the experimental forest was established, the road that we'll walk on for just a second was designed to go all the way out the valley and tap into a bunch of tributaries that drain the north and south-facing hill slopes that they were going to gauge and experimentally manipulate. The concepts of those manipulations occurred back in the early 1900s with the establishment of the first paired watershed study in the world in Wagon Wheel Gap, Colorado. Those experiments were repeated at the Furno Experimental Forest in West Virginia and Coweta Experimental Forest, the hydrologic lab in North Carolina. So those were the models that were used to establish this site. It was, as those were being constructed and calibrated, so they were monitoring them for some period of time, that's when Herb Borman was poking around with his students, came over from Dartmouth. He actually was at, now I forget where he was in Georgia. Emory? Emory.
That's his first teaching position.
I think he was at Emory at the time when he would take students to Coweta, and that was the first place where he saw this concept. And when he came to Dartmouth, he sort of tucked that away, and he learned that this site was in operation. He used to bring his class here, probably plant ecology class and other classes that he was teaching at the time, and that's where I think he started to get this idea. And he wrote a letter to Bob Pierce. This is probably pre-Gene Likens. A letter to Bob Pierce with this idea. Do you know the date? 1960. So it was at that time where the Hubbard Brook ecosystem study concept was developed, but that was piggybacked on these Forest Service experiments that were beginning at the time. And so I think the synergy was just right to begin that. And then Gene Likens came along to Dartmouth, and so he had the water background, and Noy Johnson had the geochemistry background, so the team sort of fit together nicely to do this work. So anyway, because these sites were established to do hydrological studies, some of the first research that came out of the watersheds were very simple studies that looked at how much water yield response there was after the forest was manipulated. And the manipulations were the clear cut that you heard about. It was actually a clear cut and an herbicide treatment for 3 years. So what happens if we remove vegetation altogether? There's no transpiration. And what happens?
Screws up the water cycle.
Yeah, so what part of the water cycle?
Higher flow.
Higher flow,
more erratic
right?
flows, probably.
So if you don't have the trees removing water, the only place for that water to go is out the bottom of the watersheds in stream flow. And they looked at that on an annual basis for the most part. And they looked at the different treatments. So then there was the Watershed 4 experiment that was strip cut about 1970, and they looked at the response in that site. Then there was a whole tree harvest experiment, Watershed 5, in 1984, 5.
Yeah, 83. 5.
So there were these different experiments that were designed to be a little bit more silviculturally oriented than that first one, which was really the ecosystem study experiment where they harvested an herbicide.
But didn't they get terrible flooding and washing away of soil?
So that's a really good point. So that was part of the objective of the Forest Service initially, and the answer to that is no. The changes in the high flows were significant if you think about how a statistician thinks about significance, but they weren't large flows that affect the channel reworking, moving sediment around, geomorphologically effective flows. So there were increases, but they were small, and almost all those increases were summer-fall increases. So the smaller storms were larger after the harvest, but not large enough that it did much in terms of high flows.
Was any of this early work motivated by flood control?
Yes, that was the entire purpose of that early work. So again, motivated by the Omnibus Flood Control Act in 1936, that was why they established the site here, because they had no scientific data in this region. So that was the reason to do the experiments initially. You want to add anything?
Well, no, the question about erosion is interesting because based on some detailed measurements of the soils, it seems like the soils have been pretty well intact for a long time, pretty much since the glaciers. So anything that could move real easily, or is it really erodible, the glaciers had taken care of that. And so along the east coast, when you think about sort of the erodibility, that glacial line, once you get south of New York pretty much, that's where you run into the really erodible soils compared to what we have up here.
Another question, wasn't there a topsoil of humus, humus material that was built up?
We did. We lost a lot of this type of stuff. Yeah, with those higher flows. It was one of the few times that it was detectable, but that was the only time it was even really detectable was at these peak deforestation experiments.
And the soils for these experiments, particularly the first one, weren't disturbed. So someone walked around with a chainsaw, just fell the trees, and they stayed in place. Mm-hmm. So there wasn't logging machinery that drove all around.
The first one they just sprayed.
That's
they
right.
Just laid it down and sprayed.
That's right. Okay. And then the other two, they did extract the trees. But the first one, the strip cut, the disturbance was pretty minor, and they left a buffer along the stream, so a forest buffer along the stream. In the Watershed 5 experiment, it was a whole tree harvest, so there was a machine that went to every tree bowl, grabbed the thing, cut it off, and so that machine had to go to every single tree bowl in the forest. There was much more disturbance in that experiment. But peak flows, there weren't real detected differences in peak flows, but there are differences in the long-term response of that watershed that that's still a puzzle.
But Wayne's paper showed that when you had huge precipitation events, that's when you got a change. I mean, not just a regular precipitation, not just a heavy, but when you got the drastic, like 3-inch rainfalls in a very short period of time.
So I think in general that's a bit of a myth. When you look at the literature, the larger the event, you get enough water on 2 watersheds, and one of them was just harvested and the other one still has trees on it. That event brings enough wetness to both watersheds that they respond about the same. Statistically, the larger events, you can't separate out the difference. It's the smaller ones when you're coming out of the summer and the watershed that has the trees is transpiring like mad, drying out the soils. The other one is wetter. So now you put a little bit of rain on these two. The one that was a little wetter responds with a slightly higher peak. So that's the general response. And you see that going all the way back to the Wagon Wheel Gap experiment in Colorado, and the Coweta experiments, and the Fernal experiments, and just about all the experiments that have ever been done.
Around the world.
Yep.
Yeah.
So that's the general response. Now, what Mark and I have been exploring recently is a lot of that early work was either looking at the maximum annual flows, the highest flows, or the annual discharge. So if you take the flow every day and you add it all up and you look at how much water there was at the end of the year and those changes year by year, that was sort of what those historical studies looked at. We are beginning to look at more the variations in the flow regime, and there are differences in the flow regime at low flows and at high flows that are still detectable in these experiments today. And that's actually ongoing work that's not published yet that Mark will be presenting some of it this week, and then I've been working on some of it as well. So the story's not over, I think. And your question about the erosion, the increases are not that significant, but they're there, I think, still.
Well, I mean, the real question was is what kind of timber harvesting techniques are best in terms of least environmental damages, that kind of thing.
So when you're talking about hydrology,
Okay.
you're not. I don't think there's going to be a huge effect. It's the biogeochemistry that's more the issue, and that's what really we learned at the ecosystem study. It was the biogeochemistry. So if you were on the other walk with Charlie, that's probably what he's talking about. But really, I think that you're right, Larry. It's about what is that management effect, and from the hydrology and erosion perspective, it's pretty minor. Now, some of it is a bit of luck. So, the Watershed 4 experiment, they left a buffer of trees around the stream. They did the same thing in another experiment like this in Pennsylvania. It was a little bit later in the 1970s. And that buffer of trees standing up in the middle of a clear cut was susceptible to wind throw. And so, in that experiment, when they had a bunch of trees that blew over, right in the channel, there were huge pulses of sediment that came out. So there is a little window there where the system is pretty susceptible. And it depends on, obviously, the type of management. So anyway, that's kind of the history and why the experimental forest was established and why that sort of framework was here for the Hubbard Brook ecosystem study to piggyback on. And we're doing lots of work now in the small watersheds that I like to talk about it as sort of opening up the black box, because these historical studies were just looking at input-output relationships, and there was not a whole lot of investigation of processes within the catchment. And there's a lot more of that today than there was at the establishment of these sites. So Mark and Heidi have been looking at transpiration response. JP Gannon's a graduate student with me. We're looking at groundwater dynamics in the catchment, trying to understand during storms in the subsurface, where are the active zones in terms of the hydrology. So where is the subsurface flow zones that contribute to stream flow? So we're trying to identify these and map them out. So that's kind of some of the new work that's going on today, is to really kind of get a handle on the internal processes that give rise to the response at the bottom of the catchment.
Which seems interesting because in my old property in the wintertime, with freezing and thawing, it wasn't a uniform flow of water in the groundwater. It was channels of water that were here and there through the topsoil.
Yeah. So JP, do you want to say anything about some of the work you're doing or what the objective is? I'm putting him on the spot. I told him I'd do that.
So we, the experimental watersheds have always kind of been thought to be a uniform soil type, this well-drained spodosol, where you have sort of vertical horizonation going down the profile, and it's extremely well drained, which means that when it rains, the water moves down slope without much hindrance and goes right to the stream. You don't see saturation, you don't see water table building up. But several years ago, one of Kevin's students started to put wells in the summer and found saturation, found water table in places throughout the watershed, and that kind of changed how they were looking at the soils and water table in the catchment. And did that with another student's work where they identified several different changes in soil morphology where you can, so basically you dig a pit, dig a hole in the ground and see the coloration of the soils and the horizonation, and it varies a lot. It's not the same everywhere. It's not even close to being the same everywhere. And those variations that they saw, I've found that they're extremely well tied to how those water tables behave. So you can dig a hole and look at what the soil looks like and then say, okay, this soil has water table this percentage of the year and this is what the fluctuations look like. And so that's what I've been trying to do, is try to tie the soil morphology, so how these soil pits look, with what water table fluctuations are doing in the subsurface. And then now a student that just finished has been able to map where those soils are in the watershed. And so now we can look back and say, you know, with this much rain and this much wetness before the rain, what soils and where are they in the catchment are going to have water table, and start to get at what how flow is generated to these streams, and maybe how the previous wetness and then storms affects the chemistry of the water throughout the network, not just at the outlet. So it's kind of like Kevin was saying, open up the black box and sort of looking at smaller scale processes that integrate to the larger.
So rather than assuming average soils that look the same everywhere, or what the carbon content is of the soils on average for the watershed, we're now learning a lot about the spatial distribution of these things. So this means that this might help us identify where salamanders are. This might help us identify where the hot spots are in gas fluxes. This might help us understand where the carbon is stored and how it's going to interact with changing precipitation dynamics that are going to affect the water table development and ultimately export or retention of carbon in sort of a climate change setting. So that's kind of what we're aiming toward with this process-oriented work inside the catchment, is trying to understand the spatial relationships that link hydrology, soil development to some of these other ecosystem processes.
Two questions.
Okay.
Is this all glacial till on both sides of the valley? I mean,
No. There's till, yes, but there's also some stratified glacial deposits that are not till, but that were water worked. So
okay.
in this region in particular, there are cane terraces,
Yeah.
and it's not all till, but all glacial deposits, yes. Heidi, did you want to add to anything we were just
It
saying?
was a question on that. But,
Okay.
did you have another?
No, I just,
Oh, I was just wondering about, do you know why you have these different depths of groundwater fluctuation? Is it geology, slope, position, vegetation?
Seems to be complex relationships between different topographic metrics. So we can predict where these are really well. If just going out and standing somewhere and looking around, you can say, this is the soil that I'm going to see, because you have a big drainage area and then the slope becomes less severe, and so you can imagine water pooling there, kind of.
It's more topography than
Yeah, it's more,
underlying
but it's topography, but it's also subsurface topography. So if you have somewhere like where there's a bedrock outcrop right above you, that's going to supersede any other kind of control, right? Because you have a lot of water coming off that bedrock. It's like putting a parking lot upslope. And so the student that just finished had worked all of this into a model that is able to predict pretty well where those soils are in the watershed.
so that's a good question, and it relates to Hank's question, because we're doing this in a catchment that's dominated by glacial till. Once we kind of get into these deeper deposits, I don't know how well that's going to work, and there's enough variability even in a till that the topography doesn't always predict it, you know, very well. So we have a lot of variability in how well we predict, because there is a subsurface control that's related to the type of till, whether it's a basal till or an ablation till, or as we work our way down into the valley where we are here, you're going to have more water worked kind of stratified drift deposits that are going to behave very differently. So one of the goals, and one of the things that we can talk more about when we get to the main Hubbard Brook, is we're trying to take this model that we've developed in one of the watersheds, one of the reference watersheds, and extrapolate across the valley, and we're going to be wrong in many places. And then the question is, how do we improve this model so we can do that? We've been working a little bit with the White Mountain National Forest. This is the last national forest east of the Mississippi to have a soils map. And so they're doing this right now on the National Forest. They're coming to the Hubbard Brook soon to map in the Hubbard Brook. And we've been working with them with our sort of process-based model and their sort of traditional soil mapping approach, so we can bring these things together and converge. So I think that's pretty exciting. And I think it'll help not just in how we understand the ecosystem in terms of pattern and process, but also in management. And that's obviously what the White Mountain National Forest is interested in. So,
Do you attempt to map the underlying bedrock with a view to predicting?
we would like to do that, Ted. That's a really a huge challenge. What we have done, actually just 2 weeks ago, we repeated one of these. So not this snow season, but the previous snow season, JP and a colleague of ours, a geophysicist from the Cold Regions Lab in Hanover, brought over a radar that penetrates into the ground, and we were trying to map the bedrock depth and topography. And we did it during snow because it's easy to drag the radar around over snow. He came back 2 weeks ago, and we ran transect along some roads at Hubbard Brook, including the entire Hubbard Brook road from the beginning all the way to the end. We tied the thing to a truck and drove the radar all the way out, because the road intersects bedrock outcrops, so we can calibrate the radar signal at certain places. And so that's a goal. And it's an important issue from a hydrologic perspective, because ultimately one of the things that hydrologists have to do all the time is tell people when it's going to flood somewhere. And all of our models tend to be pretty shallow, and they don't include this storage that goes down to who knows where. And so that's what we're trying to figure out, is how much water can these watersheds actually store, and for how long. So Mark and I have been working with water isotopes, so we can sort of fingerprint water from rainfall and track its movement through the watershed to the outlet. And we're trying to do this to figure out that very simple question of how old is the water that you see in the stream? Any guesses how old you think water would be in a small stream like this at Hubbard Brook?
60 days.
60 days? Huh? Well, the answer to that question is there's not an age, there are multiple ages. So if I take a sample in that bottle of water, there's some water that could be hundreds of days, maybe tens of years, 100 years old. And so there's this distribution, and where the mode of that distribution is important. Right. So that's the question that we're trying to address, because ultimately the folks that are interested in weathering and the biogeochemistry and the element cycling that goes back to the beginning of the ecosystem study need the answer to that question, because the weathering rates are partly dependent on the water cycling rates.
So you need to know your turnover times.
So that's one of the things that we're trying to address here.
Preliminarily, 6 months.
6 to 9 months as a mean. So if you took all those ages of that,
Right.
yeah,
That's the peak of the curve.
yeah, something like that.
Doesn't that vary enormously with how recently there's been a rainfall?
Yes.
How much
That's right.
rainfall?
Yes, so the distribution itself is not a stationary distribution, meaning that at any one time the mean shifts around a little bit.
So you come up with monthly means, based on the rainfall.
We're not there yet, but yeah, we'd
The-
love to. yeah.
Actually, the mathematics to do this time variable, it's
complicated.
very complicated.
Yeah.
We have an Italian visiting PhD student whose lab group is they're the experts on this technique right now, and they're here to help.
Wow.
So
I have one more question.
Talk about differential calculus.
It rained 1.4 inches of rain yesterday, a few miles from here. Why is the brook so low? What's the,
you said yesterday?
yeah.
We had 0.2 of an inch here yesterday.
You had 2
So there's part of the answer to your question.
Yeah, I was only down here about.
So one thing that you might ask us is, how well do we know our inputs? We can worry all about, this is easy to measure.
Yeah.
It's very easy to measure flow in the stream, and we build really nice structures to do that. It's actually not as easy to measure rainfall. You think it is because you have to put a can out there. But the cannon is this big, and the surface area, the whole Hubbard Brook watershed is 35 square kilometers.
Well, you know that if you're a car driving down Interstate 93.
If
because,
we had a radar
you know,
that we
one
could park
quarter
on the
mile,
ridge, we
it's-
would
you
probably
can't
know
see
the
it,
answer to
another
this, but we
quarter
don't.
mile and it's not
So-
raining.
How many weather stations do you have in the watershed collecting water rainfall data?
Nick?
Precipitation is 25.
Oh, there you go.
Oh,
25
25.
rain gauges?
Yeah.
24.
So there's got to be at least one in each sub-watershed.
Usually about 3.
Yeah,
different
and then we use those to
Yeah,
sort of
different
aerially
elevations.
weight.
Yeah.
But that aerial weighting does not account for the topographic effect or the storm track trajectory. And Mark's been playing with some different ways of coming up with averages, and it doesn't make a whole lot of a difference. So we actually probably do a pretty good job of that here, and I'm exaggerating a little bit. But there is spatial variation that in places where we don't have gauges. So it could rain, you know, on Mount Kineo and not, you know, on the south-facing watersheds, and it might miss our gauges on the north-facing watersheds, and we would never know it. So when we're trying to do work at the full valley scale, we have very poor control on the inputs.
Could you do that with radar? I
Yes.
mean, you look at the radar
They're very
and by
expensive, Larry.
the intensity there. You can,
Yeah, some of the next rad stuff though too.
And they
yeah.
need to be calibrated too with
Right, with-
you know, ground measurements.
Yeah. We overmeasure precipitation. We do. Like Kevin had said, we can remove maybe half of the
For our gauged watersheds.
for our gauged watersheds. We overmeasure, but the benefit of that.
He
What's
wants
that?
to remove them.
No, I won't go there because what Hubbard Brook is good for is being able to answer that question. We need to overmeasure so that we can tell somebody who's trying to measure, you know, something else, what's the minimum you need for good information.
But the folks that actually do the weekly measurements want less.
That's right.
So why don't we take a walk?
Yeah,
We have
yeah.
we're gonna try to find a spot for Charlie to tell us a little story as we walk. We're gonna go back out, scoot by the barn.
When you see the ice storm, today the ice storm dropped, when they showed the ice storm in January, and it was 9 months later when the nitrate peaks started. That the water displaces stored water, and so the water that's moved in is rarely water directly from the rainstorm. It's water that's infiltrating and pushing old water up and into the stream.
Except we have overland flow that goes directly into the.
But that's very small part.
This is another terrace, which has been sculpted down at some point by the Hubbard Brook.
Right. Yeah. So we're entering into the main Hubbard Brook paleo kind of floodplains. So these terraces.
Is that the main Hubbard Brook over there?
That's Norris Brook.
Okay.
We're the same one we were just standing on.
yeah.
We'll end up at the main Hubbard Brook, which is it's a nice looking stream and now it's quite impressive.
The way that this is constructed, you've seen the weirs where we have theoretical relationships. We just need to know what the height is there. Here we have to establish a relationship between the height of the water and the actual volume that's going past here. And so that's tricky, especially when it's flowing fast. But
This time you can get down there and walk around in your sandals and measure it and it's easy, but not in the winter.
yeah. And so that's where Nick has installed this. And so I'll let him explain what this is, what this cable is.
Yeah, so ideally we were going to set up this cableway on the same transect that they use down there. We have a pressure transducer that's measuring depth stage every 15 minutes. And they had taken some discharge measurements manually by weighting the stream in that same location, correct?
Yep.
So they already had started that lower end of this stage discharge relationship. But the site just wasn't going to work out with the topography and the materials that we had, and I tried to accumulate everything that had been purchased and piece it together. And
We bought like
this was kind of
one
a
thing
compromise. Yeah.
like cable one year and
Yeah.
something else another year. We had like no money to
Yeah.
only a couple $100, but we didn't have extra.
Yeah, so I basically had a couple $100 too to get the rest. So we bought concrete, we bought the post, we bought the rope was actually purchased already, and then we used this hemlock across the stream as our anchor point on the other side of the stream, just because putting another concrete base over there just wasn't an option. Yeah, but so like they mentioned, right now we would wade the stream and make a manual discharge measurement, but this is mainly for those high flows, those big flows that come down that it's just not safe to get down near the water.
How high was it at Irene?
It was pretty high, yeah. I mean, you can probably still see remnants of...
Halfway up the bank?
It's hard to tell, yeah, it's hard to tell, but it's definitely...
How many inches of rain did you record for Irene?
Irene itself, I think, was on the order of about 5 inches, but we had, in the weeks leading up to that, we had 2 other significant storms that saturated
Everything
the
was
soils.
saturated.
Yeah.
Which was like the 70s. You had the same thing happen when we had the flood in the 70s. Which was
5 inches is not a lot compared to what we saw elsewhere.
So you want to explain what you're going to do with this?
Yeah, so essentially... So essentially we'll place what's called a sounding reel on this portion here, and we bolt it down, and that's just a spool of small diameter cable. And then there's a pretty cool machined triangular pulley system sort of thing that sort of cradles on this main wire. And then the sounding reel goes to the bottom pulley, and then down from that main triangular piece we hang a velocity meter. And the idea being this rope would be used to kind of pull it out to a known set point, and then we drop the velocity meter down, we make a velocity measurement. We're measuring the area of the cross section as we go. So with that area and the velocity, you get a discharge in cubic feet per second or whatever you're measuring.
So do about 20 to 25 measurements across the channel.
And that velocity meter has a weight on the bottom that's 50 pounds, so it's a big, heavy thing that you got to kind of muscle across that.
This is the same procedure that the U.S. Geological Survey uses on all their streams to get the actual measured volumetric flow rate. And what you get real time on the web is just a conversion, because they measure stage, they know the relationship from their actual measurements, and then they can just give you a direct measurement of volumetric flow or discharge. And so that's what we have to develop here. We have to develop that relationship.
Question. What? You go first.
Okay,
You're lead.
Will you use this for both low flows and high flows, or will you do this is just for the high flows and then you'll do the more traditional?
That's a more accurate way. Yeah. And our streams are pretty flashy, so this is a bit of a coarse measurement. You measure the stage when you start. It may not be the same as when you finish. So, you know, if you get really good, you can do it quickly.
How frequently are you doing those measurements?
It's just, yeah, it may be a handful of times per year.
It's really only when you're getting some sort of precipitation event that's going to bring the water up?
Yeah. Yeah, so maybe a rain on snow event, like in the winter, when the soils are frozen and everything just runs off.
So you guys are one of the rat teams that run out here and take care of it.
Oh yeah, I'm one of the original rats.
Large rivers, like on the Pemi, they'll hang off bridges. Other systems, they will actually have cable cars that someone sits in as they scoot out and make the measurements.
I guess those are outlawed now.
Yeah, you can't
They still use them, but they're not building new ones. They're not. Yeah.
You guys are gonna ride out there.
to come up to the Oak Bridge in Plymouth.
Yes.
And put his cable onto the edge of the railing.
And they have trucks with a little system that they could just drive along and measure it. And they also have acoustic Doppler systems with GPS and a float, and you can put it across and just pull it across and pull it the other way, and it gives you the
You get depth integrated velocity.
a two-dimensional velocity distribution. They're very expensive, and they don't work very well in these sort of cobbly settings, and so.
So that brings up my question. Why wouldn't you go down there and make a rough weir with all those rocks?
A weir?
Yeah.
What are you doing? It will move around, and it's. This is a fairly tried and true approach that you can use a natural cross section. If you make enough measurements, a lot of these big rocks aren't going to move. So, but you make a lot of measurements, and you keep that relationship. You keep modifying that relationship as it changes.
As the channel keeps changing every storm.
And it doesn't change that much, you know, in these very large storms. These large boulders won't move.
Yeah, but the little ones there are controlling it.
Yep.
So we have to update that relationship, constantly updating it for that reason.
Boy, I'd get a sack of concrete.
So the one problem with that is that the way that those work, the weirs work, is you have to have still water, not turbulent water. So you'd need to set up like a really long flowway.
The largest flumes you would see are on streams about a third of this size.
But for a triangular weir.
That will not work. A flume, a flume, like a.
Yeah.
But the largest streams you would see them on would be, yeah, a third of this size, and they're very difficult to maintain, and they blow out, and you lose this infrastructure that you invest in.
Is there a fixed rate between the depth and the flow?
No. It's a relationship that you have to establish.
Yeah.
Right.
Well, having established it.
Then it's fairly fixed until the form of the geometry changes.
Why not just put a post in there so you can read the depth?
That's being done down there, and it's recording every 15 minutes. The depth. So we'll take that depth and relate the depth to the measured volumetric flow, and then we make a relationship of that. So then we can just measure depth and calculate the volumetric flow.
So, for whatever it's worth, I'm the historical ecologist for the project, which is all old hats, so I'm not around very much. But just a few quick things. The valley, that is the Hubbard Brook Valley, which is this big bowl within a very narrow mouth they call the gorge of the Hubbard Brook, and then the river, or the Hubbard Brook main stem, goes out and hits the Pemigewasset River right beyond where the road hits Route 3. Actually, it goes a little bit south, and then there's some, it used to go in a different place because Route 3, and then whatever botched up the channel. That valley was granted into two towns, Thornton and Peeling, and the line is about halfway up the Hubbard Brook Road, right before the interstate crossing, just east of the interstate crossing. There was an encroachment about a half a mile where Thornton and Woodstock both claimed the same territory. And the towns decided to cut it down the middle, created a new line in about 1792, which is just when settlers came into the region. They settled farms along the Thornton side, which is right now along Route 3, and then a few farms up in the valley, including two of note, one at Pleasant View Farm, and the highest one in the valley was right where the barn is, on the Forest Service property here. The farmhouse was just across the street from it, and his brother lived in the red farmhouse that's a decrepit derelict. It's
gone, they just took it down.
Oh, the second Woodman farm's gone. Okay, those were established in about 1810. They were the highest farms in the valley. They were more or less subsistence farms, although the woodsmen's, plural, were tanners and cobblers, and made shoes. So they were shoemakers by craft, but farmers by doing everything else that they had to do around. And that farm then was handed down through the generations of woodmen, then given to a family named Norris, who only lasted there about 3 years, but did give his name to the stream that ran through one of his fields. Then continued to be down until this became an industrial valley in about 1860. There was a big mill, water mill, just below where the interstate crossing is to Mirror Lake Road. There's a hillside, there's an old mill pond down there, the foundations of the mill. That ran between about 1855, but 1860 it was rebuilt. It's at its heyday in 1880, and then kind of ran a little bit downhill, but soon was replaced by an even larger mill complex that was fed by the railroad. The railroad came up the valley in 1883. They put a sidetrack into the Hubbard Brook, following Hubbard Brook, and built a huge steam mill right below where the houses are after you cross the interstate. Basically, just upstream from the old water mill, and so the remains of both are there.
Milling what?
Milling lumber, spruce lumber, period. The big mill, which was owned by Vesey, who was a lawyer in Laconia, ran between 1906 and 1920, milling 11 million board feet of lumber per year, all of which came out of the valley. All of which was spruce.
Out of the Hubbard Brook Valley?
Hubbard Brook Valley, a little bit from Beebe, but don't worry about that. They rewrote their contract in about 1915 to take a little bit of hardwood that was growing along the roads nearby, because there was a bobbin mill right at the Route 3 crossing that was using bobbins. But bobbins don't take much lumber. They just need a little bit of beech.
At that time, how large was the spruce?
We have pictures of the mill yard, and they're good 1.5 to 2 foot butts. Nothing extraordinary, but there's 11 million board feet of those sitting each year in the mill yard. I assume there were a few larger trees at some point, probably cut very early, because that was the milling in the 1910s, but the earlier milling in the 1880s had taken the cream. None of this was clear cutting. It was all what we would consider high grading, taking the lumber that they wanted that was easy, which was spruce of a certain size and and that was all put on the train in the 1910s and taken down to the south, Boston and areas to build. As we like to say, well, that wasn't. Most of the timber that went down in the 1880s went down the river to Lowell and became the Back Bay. The lumber that went into the building there, but a lot of the building in the early 1900s was wood dimension lumber that came from the White Mountains. This was only a small operation. The operations in the Pemigewasset Valley, the Henry operations there are the real giants of lumbering. But this had its own well-defined history. Mills that we know about, timber that we know where it came from, and believe it or not, we have numbers for all of those. Literally, how many board feet, how much stumpage, what the timing was of taking different things out. The only thing we were missing is really spatial control there, and we're getting that finally. There's a student working this summer that's looking at the tree ring history throughout the entire valley to see where there was disturbances in what years, going all the way back to 1790s. Okay, so this is farmland. Beyond the farmlands up there, we also had a tannery that was on the outlet of Mirror Lake. This was a really good hemlock area, so there was a lot of hemlock taken. We have the books from the tannery, so we know how many, call it board feet, it really isn't. It's cords of bark that can be related to how many trees they had to take down. We knew what lots in the valley the tanner owned. Campbell's owned the tannery, cut here, used all local supplies, so we have bobbin mills, tanneries, spruce timber, all revolving around economics of the valley before any experiments were done whatsoever. And that's what historical ecologists look like.
So from 1790, and then it picks right up on what John talked about today, the Sycamore battles, inventory across the valley. So it was really a good record of forest history.
Did sheep ever come into the valley?
What sheep did to a degree, and about sheep declined in the 1840s due to competition from Argentina and a tariff on wool. But they continued here during the Civil War on the property just north of Mirror Lake, and those fields, which are now plantations, which are falling to pieces, pine plantation, are the old sheep pastures.